I can add mod 2, bk plus 1 on both sides. So actually I don't, from now on, I don't even need to write mod 2. Because I'm going to assume that these bit operations are mod 2. And once again, I emphasize, because this is a finite field, all the usual operations apply. So in other words, it's commutative and associative, so in other words, if I do this, and then I do this, it's the same as, because it's associative, doesn't matter what I do first. So in other words, I can take these mod 2 first, and then do that, or I can take them all together, it doesn't matter. Anyway, in mod 2 arithmetic, what is this? If I have,
0.
It's always 0, right? Because this is always the same as that. So 0 plus 0 is 0, and 1 plus 1 is 0. So this is always equal to 0. So in other words, in 1 plus b2 plus b3 plus bk plus and so on, in mod 2, this has to equal 0. So if you think back to, let's take a step away from mod 2 for a second, what does that mean about this sequence? The sum of the sequence must be 0 mod 2, which means that it's, what values are 0 mod 2? 0, 2, 4, 6. So this must be even. So in other words, there must be an even number of ones. So a very simple way to check to see if a single parity check is valid, check to see if there's an even number of ones in the string. If there is, then actually what you can say is that if there is not, if b1, b2, so on, bk plus 1 has an odd number of ones, then you can say an error must have occurred. At least one error must have occurred. Okay, suppose you take this and you say, you add them all up and there's an even number of ones. Can you guarantee that no error has occurred?
Of course not.
No, why?
Because like the number of errors, if it's a mod of 2, I mean, if the number of errors mod 2 goes to 0, then you don't know how many errors are there.
That's correct. So if it turns out that, actually it's obvious that there's an even number of errors. So if you start with this string, if at the transmitter, this is valid, so the sum of this is even, and then I flip any 2 bits, then the result will also be an even number of ones. So there's such a thing as an undetected error. So any even number of errors is undetected. So single parity checks, where do they work really well? They work really well if you expect the probability of error of any individual bit to be extremely low. So the probability of any individual bit, if it's extremely low, let's say 10 to the minus 9 or something. So if I have a group of k bits, and individually the probability of error is 10 to the minus 9, then the probability that there is an error in the string is approximately k times 10 to the minus 9. The probability that there's 2 errors in the string is like the order of 10 to the minus 18. So if a single parity check worked really well if the probability of bit error is extremely small, because in that case the most likely event is no errors. It is very unlikely but possible that you'll receive 1 error, and it's essentially impossible that you'll receive 2 errors. So you can In the rare events where you get one error, you can detect that, and you can be reasonably assured that you won't get 2 errors. So for instance, 10 to the minus 9, let's say that, let's say I have a transmission scheme which transmits 1 gigabit per second. So at that rate, I would expect 1 error about every second. In a single parity check code, a single parity check code would work pretty well there because the probability that I would get 2 errors in any particular block, that would probably occur about every billion seconds. And a billion seconds is, it's only over 1,000 years. So it's extremely unlikely that you would get 2 errors. But 1 error would occur about once every second. So that event would be important to detect. Okay, so more generally, why do we know this can detect errors? So any even number of errors is undetected. Turns out a single error or any odd number of errors is detected. But for our purposes, it only really matters that a single error can be detected because the probability of 3 errors occurring is far, far, far less likely than 2 errors. So if I give you a code, in other words, if I gave you the single parity check code, and I asked you how many errors can this detect, we know that it can detect 1 error. And then I ask you, can it correct any errors? We need a systematic way. Another way of looking at it is this. Let's say you didn't just have a single parity check code, whose properties are fairly easy to identify. Let's say I gave you a different code, and I said, how many errors can this code detect? The tool by which we explore whether a code can detect errors or not is called the Hamming distance. So let's start being a little more formal now. So a code, C, is a set of binary sequences. I'm going to say that the length of that code is implicit, let's call it n. The length of the code is n. So a code C is a set of binary sequences of length n. So in other words, you can write C as a set, and C is a subset of binary elements, the n-fold product of binary elements. So this, this notation just means the set of all binary vectors of length n, and C is some subset of that. A code word, if there's some small c in the big code C, actually I'm going to use sort of script notation to distinguish this as a set. If C is in the big, if some small c is in the big C, then small c is called a code word. So, the Hamming distance between two code words is the number of positions in which they differ.